So 4.2 is going to lead us to figure out how do we find the area under the curve. And everything's really based around a limit definition and then some summations. So let's talk about what a summation is. So you're going to see another Greek symbol here, and it's the capital letter sigma. That lets you know you're taking the sum of some stuff. So we're adding a whole bunch of stuff together. And we're going to see some variables in here. So like down here in 5, they're using the variable I. In 6, they're using k. And they're giving you a starting point and an ending point. So let's say we just had I. I is pretty common to use in sigma notation. And let's say we're starting from 1 and we're going to 7. So what this means is we're going to replace I with 1. And then we're going to go 2. So this is what we get when I is equal to 1. This is what we get when I is equal to 2. When I is equal to 3, then we replace that with a 3. When I is equal to 4, then we're going to replace this with a 4. And then a 5 when I is equal to 5. A 6 when I is equal to 6. And then a 7 when I is equal to 7. So we're really just adding, in this case, the numbers 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Which would give us a total of 28. So we're really just finding some kind of sum. We could change this a little bit. Suppose we wanted I is equal to 0, and we're going to go to 3. And we had a different expression here. Maybe it was 2I minus 1. Then that means when I is equal to 0, if we were to plug a 0 in, we're going to have 2 times 0 minus 1. So there's your first term. And then when I is equal to 1, we're going to replace that I with a 1. When I is equal to 2, we would replace that I with a 2. And then when I is equal to 3, we would replace the I with a 3. So you can see how these terms in this summation is a little different than what we had in the last one, just because that last one was really simple. This guy's a little bit more complex. So if we were to simplify this, we've got negative 1 plus, that's going to be a 1 plus 3 plus 5, which will give us a total of 8. So our first step in this section is really understanding what does all the sigma notation mean and how do we go about solving something like this. So if we were to look at that next one down here, number 5, we're starting with I is equal to 1 and we're going up to 6, and that's the expression we're substituting in. So our first term is going to be 3 times 1 plus 2. That's when I is equal to 1. And then if I is equal to 2, when I is equal to 3, when I is equal to 4, when I is equal to 5, and then when I is equal to 6. So now we're going to go back and simplify. This first term is going to be a 5. 6 plus 2 is 8. That's 11. 14. 17. And then 20. So if we were to add all of those terms together, we're going to get 75. So you can see that this can be a little bit tedious. There is a way to do this in the calculator. So go ahead and get your TI-83 and 84 out and we'll talk about how to do that. So to do this in the calculator, we're going to have to find the sum of a sequence. So if you hit second and stat, we're going to go over the math. We want to add a whole bunch of things up, so that's why we're going to use the sum here. And then we need to write out what the sequence is going to be. Sequence just means we're plugging one number into an expression, and then we're plugging a different number into an expression. So we're going to get a whole bunch of different terms to add together. So if we go to second, stat, and then over to ops. Option 5 on my calculator is a sequence. So we're doing the sum of a sequence. We have to tell it what the sequence is. So in this case, our sequence was 3i plus 2. I'm going to use x instead of I. So there's our 3i plus 2. We're using 3x plus 2. Now you have to tell the calculator what variable you're using. So we're going to do comma. Our variable is x. And then we need to tell it the starting point. So we're starting at 1. We're adding up to 6. And then we are going up by 1s. So we're doing the sum of the sequence. So we've got 3x plus 2, variable x, starting at 1, going up to 6, going up by 1s. So this is going to plug 1 in, then it's going to plug 2 in, and then it's going to plug 3 in, and so on, all the way up to 6. And then it's going to add all those numbers together. Hit enter. You see we get the same number 75 here. So we can do this on the calculator and we can do this on the by hand. Let's look at number 9. Number 9's got that variable c. So I want to talk about what this means. We are starting at 0. They're using k here instead of I. So c is just some constant number. So when k is 0, notice there's no place to put the 0 in here. So we're just going to get the number c. When k is 1, we're going to get the number c. When k is 2, there's no place to put a 2 in. There's no k here. So we're going to get the number c. What do you think would happen when k is 3? We're going to get the number c. What happens when k is 4? We're going to get the number c. And then when k is 5, we're going to get c. And when k is 6, we're going to get c. And then when k is 7, we're going to get c. So if we were to add these together, we have 8 c's. So this would be 8 times c. This one you wouldn't be able to do on the calculator because it's using a variable here. Let's look at number 6. So number 6, we're starting with 3 and we're going up to 9. Let's do this guy in the calculator. So our expression is k squared plus 1. We're going to go to second stat. Go over to math. We want to do the sum. That's option 5. Second stat, ops, sequence. Our sequence is k squared plus 1. So now let's talk about some properties of summations. So here's the theorem. Theorem 4.2 gives us some properties. We've got shortcut formulas for if we want to add from 1 to some number n for I squared, and I cubed. And then we have this constant one. So I want to talk about this guy first, and I'm actually going to go back to one of the examples that we did. I'm going to tweak that example just a little bit. We went from 1 to some number up here earlier. I think it was 7. So, and I'm starting at 1 here, and a few pages back we actually started at 0. Notice all of these start at 1. That's super important to use these. So we're starting at 1. What this means is when I is 1, we have C. When I is 2, we have C. When I is 3, we have C. When I is 4, we have C. When it's 5, we have C. When it's 6, we have C. And when it's 7, we have C. So if we count how many we had 7 of those. So let's throw a row number in there. Say we have the number 2. So then this means when I is equal to 1, we have the number 2. Well, when I is equal to 2, there's no I in this expression, so we just have the number 2 again. When I is 3, we have the number 2 again. When I is 4, we have the number 2 again. And then when I is 5, we have the number 2 again. So we have 1, 2, 3, 4, 5 of those 2's. So we have the number 2, and we have 5 of them. So you can see where this would come from here if we were to put numbers in here, or even do it with a C notation where C is some kind of constant. I'm not going to really talk about the derivation of these. This one's kind of cool. I like to call this Gauss's expression. One of the things when Gauss was a young child is that his teacher asked his whole class to sum the numbers from 1 to 100. And, of course, the teacher thought that would take a while to do. Well, he saw patterns, and he was able to find that sum super fast. And let me show you how he did that. And he was able to come up with really something like this as an elementary school kid. He was a pretty awesome dude and led a pretty awesome life. So let me show you about this, so you can kind of see where that one comes from. So check this out. You guys are going to love this. This is awesome. So if we're adding up all the numbers from 1 to 100, we could write them out like this. Do you agree? So there's a bunch of numbers there. Now, look what happens when we pair that first one and that last one. If we were to add the first one and the last one together, what do we get? We're going to get 101. What if we were to add the second one and the next and last one together? What would we get? We're going to get 101. What about if we pair the third one with the third from the end? We're going to get 101. So if we were to keep pairing these, we're going to get sums of 101 every time. Well, how many sums of 101 do we have? We're going to have 50, because we're going to have 50 pairs. So then 50 times 101 is 50/50. So you can see where that's coming from. Now, we could rewrite this. Isn't 50 the same thing as 100 divided by 2? So we could take this idea and we could expand that to, if we stop at any n value and we start at 1, it's always going to be whatever n is times n plus 1 divided by 2. So you can kind of see where that one's coming from. So let's go back to a previous page and let's look at how we would expand these. So if we look at this one, we can split that sum up and we could look at it this way. Okay, because we could reorder, we could write all this out and we can group all of the 5i terms together and we can group all the 4's together. Okay, so that's that associative property of communication and commutative property associative and commutative properties of addition, changing the groupings, changing the order around. And then all of these are going to have a 5 in common, so let's pull that 5 out. So then both of these pieces will have a formula. So the formula for I equals 1 to n is n times n plus 1 over 2. So this would be, our n is 16. So 16 times 16 plus 1 over 2. And then the formula for this guy would be 4 times n. So I'm going to simplify that, 16 and 2 there. So this is 5 times 8 times 17 minus 4 times 16. So I'm going to get 616 for that. We can always double check this using the calculator. So we're going to do that sum of a sequence again. Our sequence was 5i minus 4. I'm going to use x. We're starting, our variable is at x, starting at 1, going to 16. The increment going up by 1s. So you can see how we're getting the same answer. Let's look at number 21. So 21, we're going to have to rewrite that I minus 2. If we were to FOIL that out, we're going to get I squared minus 2i plus 1. So then we can rewrite this. All we're doing is using properties of addition and expanding this out a little bit. And what this is going to allow us to do is to use all of those sigma formulas. So the I squared formula is n times n minus 1 times 2n plus 1 over 6. N times n plus 1 times n 2n plus 1 over 6. So keep in mind what your n is here. Our n is 20. So it's going to be 20. 20 plus 1 is 21. And if I substitute 20 in here, 2 times 20 is 40, plus 1 is 41 over 6 minus 2 times n, which is 20. 20 plus 1 is 21 over 2 plus, And this is 1 times 20. If I type that in the calculator, we should get 2470. We can always double check this using the calculator. So we're going to go second stat, math. We want the sum of the sequence. So second stat ops. It was I minus 1 squared. Starting at 1. Going to 20. Going up by ones. So you can see how we're going to get the same thing. You can see how we can use the calculator to double check our answers on these. So you're probably asking the question, where are we heading with this? Well, the goal is to find the area under the curve. So let's say we have something like this. What we could do is we can talk about rectangles. And what if we were to split this into rectangles? Maybe instead of having a bunch of rectangles, what if we only used 4? Because 4 would be a good starting place. Where you can see how this would not necessarily give us the exact area, but it would be a close estimate. Well, what if we were to, instead of use 4, what if we were to use 8 rectangles? Maybe we double the amount of rectangles. The smaller those rectangles get in terms of width, the more rectangles we have, the closer that area is going to be. So eventually what we're going to do is talk about taking the limit as the number of rectangles goes to infinity. So that's where we're heading.